This video assumes that you have viewed the previous one. We will use the data cloud shown here throughout the discussion. In our example, the data are two-dimensional, so visual inspection is still possible. In higher dimensions, that luxury disappears. Clustering algorithms do not usually determine the number of clusters by themselves. They must be told how many clusters to search for. So the number of clusters is, at least initially, a choice made by the analyst. But the same cloud can be partitioned in different ways. 2 clusters. 3. 4. 5. 6. 7. And suddenly the number of clusters is no longer obvious, almost unnatural. We now return to the 3 algorithms discussed in the previous video. They share a similar computational structure, but rely on different methods to choose the number of clusters. In all cases, we run the algorithm for a range of values of k. For k-means, we minimize the within-cluster variance and look for an elbow as k increases. For fuzzy clustering, we minimize the fuzzy-weighted within-cluster variance, a softened generalization of the elbow. For expectation maximization, we maximize likelihood and then select k using information criteria such as AIC and BIC. So although the computational engine has similar structure, the model selection logic is different. Suppose that k-means has been run with 4 clusters. To understand the criterion, let us focus on just one of them. The cluster is represented by its centroid, denoted μ1. The centroid is simply the mean of its points. Each point contributes its squared distance to that centroid. We then sum these squared distances within the cluster. This is the contribution of this cluster to the global criterion. Of course, k-means does not stop at one cluster. Each of the other clusters contributes a similar term. Here is the second cluster, with centroid μ2. Here is the third cluster, with centroid μ3. And finally the fourth cluster, with centroid μ4. The global criterion is the sum of these within-cluster contributions. UCSS stands for within-cluster sum of squares. For this choice of k, we write WCSS of 4. So far, we have written the criterion for 4 clusters. But there is nothing special about the number 4. More generally, we write WCSS of k. This means sum over the clusters and inside each cluster, sum over its points. However, this notation still depends on the cluster sets Cj. For computation, it is often more convenient to introduce an assignment variable Rij. Rij equals 1 if point xi belongs to cluster j and 0 otherwise. With that convention, we can rewrite the whole criterion using only standard summations. This form will be more convenient in the next chapters. We can now compute this criterion for different values of k. Let us place k on the horizontal axis and WCSS of k on the vertical axis. For each choice of k, we obtain one value, which gives 1 point on the graph. As k increases, WCSS decreases and in the limit it tends to 0. But the improvement is not equally important at every step. The first additional clusters produce a substantial reduction. Later, the curve begins to flatten. So we look for a bend in the curve, the elbow. In this example, k equals 3 is a natural candidate. But k equals 4 may also be a reasonable choice. So the elbow method does not give a definitive answer. It is only a heuristic, suggesting a compromise between simplicity and fit. We now move from hard clustering to fuzzy clustering. Here we ask for 3 clusters and a fuzzifier parameter m equals 2. We begin with the same data points without cluster colors. Now the colors become gradients. These gradients reflect partial belonging rather than a single hard assignment. Each point belongs to some degree to all 3 clusters. For this point, we can draw 3 spokes to the 3 centroids. The membership coefficients are shown here, 1 value for each cluster. So a point is no longer assigned by a yes or no decision. We can also display the same information numerically in a table. Each row corresponds to 1 data point, and the 3 columns show its degrees of belonging to the 3 clusters. Let us revisit the k-mean sum of squares. In k-means, each point is assigned to exactly 1 cluster. In fuzzy clustering, assignments are no longer binary. They become the membership coefficients we displayed in the table. These coefficients are then raised to the power m. Since all values lie between 0 and 1, small coefficients become even smaller. As a result, weak memberships contribute less to the fuzzy sum of squares. We can now compute the fuzzy sum of squares for different values of k. For each choice of k, we obtain 1 value of jm of k. We place these values on a graph. As k increases, this quantity decreases and tends towards 0. We may again look for a bend in the curve. In this example, 3 clusters are a natural choice, but 4 is also plausible. So again, the elbow remains a heuristic. Side remark: the fuzzifier m matters. Here we compare the real fuzzy elbow curves for several values of m. When m stays close to 1, the structure is still relatively sharp. For m equals 1.2, the main elbow is at k equals 3, with a weaker alternative at 4. As m increases, the curves become smoother and flatter. At high values, the structure is so blurred that many clusters become less meaningful. We can visualize the probabilistic model that EM generates. The data points lie on a plane, while each cluster is represented by a colored Gaussian hill. The heights of these hills now also reflect the mixture weights pi sub k. For one example point, we can connect it to the 3 Gaussian components. And on the right we now display the assignment probabilities, which are related to the heights under the Gaussian bells. In a probabilistic model, we evaluate how well the model explains the data using the likelihood. For each observation x, the mixture model defines a probability density, Pa, of x, as a convex combination of Gaussian densities. The likelihood is then the product of these probabilities over all data points. This product is awkward to optimize directly. So we take the logarithm, the log turns the product into a sum, and because the logarithm is monotone, the optimum stays the same. The EM algorithm therefore maximizes the log likelihood. We now have a way to evaluate model fit through the log likelihood. Increasing the number of components always improves the fit, but we also want to keep the model simple and avoid overfitting. This leads to model selection criteria. The Scikit information criterion, or AIC, is defined as 2p minus 2 log L. The two terms act in opposite directions. The log likelihood rewards fit, while the number of model parameters penalizes complexity. The Bayesian information criterion, or BIC, follows the same idea, but uses a stronger penalty that depends on the sample size n. Here, p denotes the number of model parameters, and this quantity grows roughly with k. We now evaluate the AIC and BIC as functions of the number of components. We are looking for a minimum that balances goodness of fit and model simplicity. The AIC curve decreases steadily and does not provide a clear minimum. The BIC curve, however, does reach a minimum. In this case, the minimum occurs at 5 components. These criteria are heuristics, useful guides, but not absolute truths. Let us now compare the methods. K-means and fuzzy clustering are geometric methods, but they are not identical. K-means suggests 3 or 4 clusters, while fuzzy clustering points to about 3. The full probabilistic model, combined with BIC model selection, points to 5 components. These methods optimize different criteria, so they are not expected to agree exactly. K-means and fuzzy clustering organize the data geometrically, while EM with BIC selects components in a probabilistic model. As the model becomes more expressive, it can capture finer structure, and therefore it may support a larger number of components. Conclusion: there are no single correct number of clusters independent of the modeling point of view. Note that likelihood, AIC and BIC, are available in standard Python tools such as Scikit learn. For other mixture models, such as Poisson mixtures, one can use libraries like Pomegranate, but AIC and BIC will have to be computed explicitly.